Okay, second lesson of probability. This is the one that makes it seem the most like this unit belongs in this course. This is the one where we talk about geometric probability. Okay, so probability, we've always been talking about in terms of this fraction so far, where we kind of have like the number of ways something can happen favorably that match what we're concerned about, out of the total ways it could happen favorably or unfavorably, kind of total. Now those quantities are both going to be geometric measurements. Most commonly area. We'll get to it when we get to it. I don't need to preview that. I think that will make sense when we get there. But yeah, remember when we're talking about this, that the things on top, the things we're counting, when I say number of things favorable out of number of things total, each one of the things in the whole sample space has to be equally likely. So we kind of have to take everything down to its common denominator before we start comparing apples to apples. Hopefully you'll see what I mean when we get there. All right, we can extend this to length. So this is the kind of the one-dimensional version of that. I'm saying we could have a measurement over a measurement in terms of the two, the two parts of this fraction that we could use to represent probability. So here we're talking about the whole sample space as the segment AD. What's the probability if we pick a random point on this segment? What's the probability it's in segment BC? Well, then the favorable outcomes here would be all of the red points essentially, which is an infinite set of points. It's all the points along that segment out of all the possible points we could have picked on that entire segment AD. So it's just these lengths in this fraction like this. This one seems kind of strange. Like, why would we have a probability? Like, who cares about picking a random point in here? What's the probability it's in here, as compared to the whole segment? I think that's true. That's fine. There's nothing wrong with that. It just doesn't seem to make as much sense contextually as the area ones. Okay, so this is the same thing. What's the probability if you're going to have, generally what this is going to look like is you throw a dart at this dartboard. You got this rectangular dartboard with a circular area on it. If you know the dart has hit the dartboard, what's the probability that it's in circle B? Like what percentage is circle B in terms of area out of the entire big enclosing rectangle? So the sample space, meaning we know it didn't fly off the wall at all. It didn't fly off the wall completely, airball kind of shot. If we know it landed in this rectangle, what's the probability it's also in here? We're going to say region B's area divided by region A's area. Usually this makes most sense to me if we're talking about darts and dartboard and stuff. Usually, or like archery, you have the rings that look like this. What's the probability it's in any certain ring is going to be that ring's area divided by the total area of the entire circle. So it's always this idea of favorable possibilities, like number of ways it could be favorable divided by the number of ways it could have happened in the first place, like total. Okay, so when determining geometric probabilities with targets, we assume that the object lands within the target area. If it's outside the sample space, then it's a case that doesn't even really fit our question. If you didn't even hit the target in the first place, then we kind of don't care about that case. We're only talking about this, later we're going to call it conditional probability, that given the fact that first we know that it did hit the target, now what's the probability that it's in a certain region? Of those darts that hit the target, what fraction of them are in such and such a zone? So that's why we're gonna only consider ones that hit the target. And this is also assuming this major assumption that all the points inside the sample space are equally likely for the dart to fall, which isn't a horrible assumption, but it's an assumption you have to kind of think about. All of the problems we do will have that assumption, so you don't have to scrutinize that assumption. You can just assume that it's true, but it is something kind of like realistically we have to be careful of. Okay, you can also do that with sectors of a circle. If you were imagining we could take this area and divide it by this entire area, if you reduce that fraction, or if you remember the way we figured out sector areas, it was always figured out as this degree as a fraction out of 360. It was always x degrees out of 360 times area equals circle area. If we're going to divide that by circle area, well, the circle areas would cancel. And really this is the same thing as just saying it this way. So what percentage is this sector out of the whole circle? Well, it's x degrees out of 360. This is exactly how they make pie charts. This is the theory behind pie charts, actually. So yeah, if I know that the dart, if this is a circular target and I know the dart hit the target, there's an x out of 360 chance that it was in this little pink zone here. Okay, this will be a much shorter video than last time. Sorry about that one, but that had a lot of setup. You gotta admit, there was a lot going on in that video. This isn't so bad. All right, so here's some actual problems. Given segment JM with these lengths, what's the probability that if we randomly pick some point X on here, what's the probability that's going to land in certain zones? Well, given this little description about point X here, point X is a randomly chosen point that lies on JM. Well, what's the length of JM? This is the sample space. It has a length of 25. I don't want to think about anything until I do this. Whoops, put that backwards. These are all out of 25. These are all going to be probabilities out of that sample space. What's the probability that X is on LM? So what's the favorable zone here? Well, the favorable zone here is LM. It's kind of like I'm thinking about the fraction LM out of JM. What fraction is LM of JM? And that just equals 10 out of 25. And, you know, I'm a little bit OCD about this. I want to reduce that. Okay. What's the probability that X is on KM? Well, the distance from K to M is 19. That doesn't reduce. And I just found that by thinking about the length that KM is out of the total length of JM. X does not lie on LM. Okay, so of all the points here, of all the length, of all the segment bits I could think about, what's favorable here? And by favorable, we mean not LM. Well, all the stuff that's not LM is over here. It's from J to L. So technically speaking, this is from J to L out of the whole thing. And J to L is 15, which reduces nicely also. All right. Okay, there's a little bit left to do here. All right, so this is a kind of unfair spinner. The spinners are not all equal areas, but we can kind of tell what they are. Oh, they didn't label E. Well, that was silly of them. What is E supposed to be? Well, this is 90, this is 50, so that's 140. Now with 70, that's 210, 315. So what's left? I think it's 45, 315, 320, 360, yeah. So they're being tricky there by not telling us, but we can figure it out because we have absolutely everything else. So given this thing, what's the probability? Oh, you know what? They're all about, you know, the entire spinner. So it's always the probability that given that the spinner lands somewhere in this area, well, of course it has to land somewhere in this area. What's the probability it lands in such and such? These are all going to be out of 360. I would encourage you to do all your denominators first on these for the entire, especially these multi-parts. Then if you get to one you're stuck on, at least you're going to get some points for having thought about it, even though you didn't really think about it. So free points for you. All right, spinner landing in region A. Well, that's 105 out of 360. Oh, I want to reduce that, but I can't do that quickly. Region E is 45 out of 360. I can do that one quickly in my head. Oh, is this just 3 of those? No, it's not. All right, spinner not landing on region D. Well, that's the rest of the circle that's not the 90 that's D. And that's, of course, 3/4. 105 out of 360. This is going to bug me. 105 out of 360, just as a fraction. You can't see that, but I can. All right, it's 7 out of 24. Okay. Sorry, just kind of bugged me a little bit there. All right. What's the probability that a point chosen at random in this rectangle, is what that's implying, is somewhere in the shaded region. So we just need to do shaded. This is what we have to find. Shaded region is our numerator. Total rectangle is our denominator. All they tell us is this radius is 3, and we're supposed to believe that all these circles are tangent and packed perfectly into this rectangle. Okay, so shaded region. For the shaded, I'm gonna do. We're gonna do rectangle, and then we're gonna subtract 6 circles. So that's what that means, 6 circles. So I got to find the area of the rectangle, and I got to find the area of each circle. Well, if this is 3, the radius of this is 3, the diameter of this circle would be 6. So that means the whole side of this rectangle this way is 12. The whole side, these are the same size circles both ways. The whole side of this thing would be 12, so 36. So the rectangle is... 12 times 36. Why do these things have to be so big? Okay, 12 times 36 is 432. Each circle, I'm kind of doing this all over the page, aren't I? Each circle is pi r squared, which is 36 pi. So rectangle minus 6 circles is going to equal 432. Minus 6 times 36 pi. So that's the whole rectangle. This is the shaded area. So this fraction, this probability, is going to equal, okay, the shaded region, which is that, 432 minus, oh, can I find 6 times 36 pi really quick? Would that bother anybody? 6 times 36 would be 216 pi. I should be able to do that in my head. 216 pi. That's the shaded area divided by the total rectangle, which is 432. And I will, you know what, as an exact answer, that's not that bad. That's 1 minus some crazy fraction. I'll see what the calculator says. Oops, mistake alert. I went to the calculator. I realized I already made a mistake, so let me fix this here. The radius of this isn't 6. The radius is 3. So pi r squared is going to be all messed up. Let me fix that. Yeah, this is all wrong. Just a second. Sorry. At least I caught it now, right? Yeah, pi r squared here is pi times 3 squared. So each circle is 9 pi. And so when I do this, so showing my work here, it's really easy to go back and make this correction if I need to. 6 times 9 pi, which is going to be 54 pi. Okay, now we'll go to the calculator again. When it comes out in the calculator, it comes out kind of strange. I actually got this thing, this negative pi minus 8 over 8, which is the same as 8 minus pi over 8, which actually simplifies to look like this, which I kind of like better. You don't have to do it that way, but I thought it was kind of cute to write it that way. Anyway, as a decimal, it's 0.607. And remember, for all of these, and this is good to keep in mind for these ones that are kind of crazy, that all probability answers should be a number between 0 and 1. So if you get a number like 4.6, you know you did something wrong. As I got this number at the end here, I thought, hey, wait a minute, I probably could have done this easier. The probability that this thing falls on one of the, in this shaded region is probably the same as if I just looked at one of these squares and said, if I know it's in this square, what's the probability it's in the shaded region? It's probably the same probability. I'm not going to figure that out now. That's just a theory that I have. Okay, we could discuss that more in class if you really like to. All right, find the probability that a randomly chosen point in here is going to be in the blue region. Okay, it's an equilateral triangle, and it has these little equilateral triangles snipped off each side. So we're going to go total big triangle is going to be total big triangle is going to be the denominator. So the whole entire sample space here is big equilateral triangle. The top here is going to be blue region. And really, to find the blue region, I'm going to say big triangle, so it's kind of like last time, big triangle minus 3 little triangles divided by the big triangle. I don't know if there's a better way to do that. Yeah, this is a hexagon, but it's not regular, so you can't really do half AP. You kind of have to just use this as a composite figure. All right, so big triangle. We need to find big triangle. We need to find little triangles. We need to do some subtraction and some fancy division. That's it. Big triangle, I kind of like doing half times base times height. That's fine. The base of that triangle, like from here all the way to here, is 14. The height kind of goes like this. Remember, this half is a 30, 60, 90, where this is 7. So this height is 7 square root 3. So this is half times 14 times 7 square root 3. Great. Oh, we should probably simplify that here. While we're at it, that'll be 49 square root 3. Then the little triangle, the small little white triangles are going to be chopped off before we make this division, is also half times base times height, but that one, the base is, well, if this is 6 and the whole thing's 14, these must have to be 4. All right, so this is, if that's 4, similarly to this being 7 square root 3, this little height in here is going to be 2 square root 3 for the same exact reason. Half times 4 times 2 square root 3. So each one of those is 2 times 2 is 4 square root 3. So this whole big thing is going to be 49 square root 3, the probability. I guess I could write it so you know what I'm talking about. 49 square root 3 minus 3 times the little guy divided by the big guy. This should reduce kind of nicely. Yeah, and wow, it does. Look at that. All the square root 3's kind of cancel each other out, and we're left with something real pretty like that. And of course, that's a fraction between 0 and 1. Okay, yeah, so don't be afraid to leave those square roots of 3 in there, because sometimes they'll help each other out and cancel each other out for you, and you don't have to worry about it. So that's it. No calculator required. Okay, great. I will see you in class.